We'll start our application of two dimensions to the energy due to gravity, or gravitational potential energy, by doing a quick review of the one-dimensional side of this. A book of mass m is lifted vertically upwards, a displacement h, and an external force, for example a person, is doing this work and it is moving at a constant velocity. So in this case the acceleration will equal 0. How much work does this external force of the person do on the book? Since we have a free body diagram over here, we'll now apply Newton's second law. And you'll notice the subscript here, y. That shows you that we're now working in two dimensions. So the sum of the forces in the y direction is equal to the applied force, the person lifting the book, minus mg, which will equal ma sub y. Again, note the subscript. That will equal 0 since v is a constant. That tells us that the applied force is mg. We'll use the definition of work. Work is force times delta x parallel. And work is mg delta x parallel equals mg delta x, since the applied force is parallel to the displacement. And you could equally have done delta y here just to reflect the fact that we're going in the vertical direction, but we just kept delta x here because that's what we've been using. And in any case, the change in x, the change in displacement, is merely h, so we come up with the work done by the external force on the book is mgh. The next step is to use the work-energy equation, where your initial energy plus work equals your final energy. We're assuming that the book started and finished at rest, so the initial kinetic energy was 0 and the final kinetic energy was 0. That gives us an initial energy of 0. The equation simplifies that the work done here by the external force is the final energy. The previous slide showed that the work done is mgh, so we have mgh equals the final energy, which enables us to conclude that the energy of a mass is increased by an amount mgh when it is raised by a displacement h. And again, just to point out, here are all these words, and they're summarized by this neat little equation. The name for the energy that is now possessed by that book, since it was raised a height in a gravitational field, the Earth's gravitational field, is gravitational potential energy, GPE equals mgh. The important thing to note, which is not obvious in that equation, is that the changes in gravitational potential energy are important, not their absolute values. H actually represents delta x, or the change in height. You can define any point to be at the 0 level. For example, the gravitational potential energy of an object sitting on your desk would be 0, but its potential energy relative to the floor would be a certain amount of joules. When we move the object, the change in potential energy is the same, whether it's moving from your desk relative to the floor or moving from your desk relative to the desk. You just have to choose where you're starting, but the change will still be the same, and that's the important quantity that we're describing here. One more thing. The potential energy of a system is conventionally defined as the negative of the work done by the field of the system, whether we're doing with gravitational fields, electric fields, magnetic fields. How do we relate this to the derivation that we just did to show that GPE is still mgh? Well, let's pull down the answer box here. Our calculations show that the work done by an external force is mgh. The conventional definition uses the work done by the force exerted by the gravitational field. A gravitational field will do negative work on a rising book, since the force is directed down and the displacement is up. So, by taking the negative of that work, you get the same result, a positive GPE for an object being raised. We'll go back to the free body diagram here to illustrate our point. The book here is moving at a constant velocity in the up direction, a displacement of h. The force exerted by gravity, that's right here, that's mg, is in the opposite direction of its motion. So the work done by gravity, once again, here we have F gravity delta x parallel. In this case, the force is negative, okay, because it's opposite the direction of the motion. So we get the work done by gravity is negative mgh, the GPE is the negative of the work, so we get mgh, which is the same answer, which is always good.